Well, hello again. Now it's time for another project, and this time we're going to be building a speaker box. Now I've got most of my test equipment set up there on the bench, as old and obsolete as it is. Right up here, let's get zoomed in. Here we can see the driver that I'm going to be using. It's a small 6-inch driver. And over there in the background is a speaker box, basically, which I'm going to be replicating. It's an old full range that I built some time ago, but now we're doing this one as just mainly a, not quite just a subwoofer, but a low range driver. Over here I've got a 1 cubic foot test box. We'll find out more about that later.
But if you're not using ZipRecruiter, you're missing out.
That's a 2.1 channel or a 2-channel amplifier that I built that I'm going to be driving it with. Here I've got a voltmeter and frequency counter. And here, very old, and you can see actually missing some buttons. We actually have one button that just broke. All the plastic has become brittle. For my frequency, my oscillator to drive the speaker. And we're going to verify the TNS parameters for this driver. Here's the driver I'm going to be using. Is a Goldwood, and there's the number GW206-8. That's an 8 ohm speaker. One thing to note for any of you novices that are building speakers, you'll see, if we can focus on it here, on this speaker connection terminal, it is labeled plus and minus. I think we should be able to see the plus there on the right side. It's not actually polarized. You can hook these up either way you want, but what is important is that they're all hooked up the same. All the plus terminals and all the speakers need to be connected to the plus side of your system. Speakers are driven with an AC signal, so there is no positive. It's just that they need to all be hooked up together. But there's the speaker box driver, and like I say, we're going to be making another one of those. But first, have to validate the speaker parameters before we can determine what size box. Regarding speaker boxes, we can see this one over here is a ported speaker box. They're basic two different types. There's sealed boxes and there's ported. And the main difference between a sealed box and a ported box is going to be the cleanliness of the bass and the loudness of the bass. Let's get this turned around. We can see the front end. You can see this was set up as a full range. So that's not really a subwoofer, but that's just a low-end driver. Tweeter there on the top. A sealed box is going to give you a cleaner bass than a ported box. And the reasons for that is the port itself causing the sound waves to be slightly out of phase, whereas the sealed box, we've only got one source coming out of the driver. When using a small 6-inch driver like this, I'm going to be more focused on volume than the cleanliness, because that's just not a big enough speaker to drive a whole lot of bass. But let's get started on the testing. It is time for the free air resonance test of the speaker. Over here I have my function generator, an amplifier, a voltmeter, and actually 2 voltmeters. 2 multimeters, we should say. One's being a voltmeter, one is going to be a frequency counter. Down here we can see there is a 10 ohm resistor that is going to be in series with the speaker, and the speaker is up here in the free air, and why it's called a free air resonance test. We're going to find the free air resonance of the speaker, and later down here on the ground we'll be using this box, which is a sealed known volume box, to be doing some other tests. So let's get started on this test. Now we're ready for the test. I've moved the function generator over to the right side, make it a little easier. This is actually the second take because my fat arm was in the way adjusting the function generator when it was on the left side. So A quick review here. We've got my amplifier that I built quite some time ago. It's got an automatic turn on. You can see the signal LED on the top and the on LED to the right. The signal LED will indicate when there is a signal which turns the amplifier on. Otherwise it just sits there and does nothing. I'm going to pause the production here just for a bit to show you the pictures of this amplifier that I built 25 years ago. I'm going to thumb through these pictures pretty quick, and if you want to get a better look, you can just pause the video. Here is a better look at the front and back panels, followed by 3 images of the guts of the amplifier. And last, we have a close-up of the power supply and then the actual amplifier module. And now, back to the production. Down here is that resistor in series. We'll be monitoring the voltage across that resistor, and it's going to tell us when we reach the resonant frequency of the speaker, which, as I said, is up here hanging in the free air. So let's get back down, focused in on those 2 meters. Well, first we'll show you the amplifier as it turns on, and then we'll move over to the 2 speakers. As you can see, we've got a power on light here, which just tells me that the amplifier is ready, waiting for a signal. This potentiometer adjusts the threshold of the signal, so small signals don't inadvertently turn it on. And this one is a delay, so that when there is no signal, it waits so many seconds before it actually turns itself off. So we'll turn the function generator on, and you see we have a signal. It has turned on, and you can see when we turn it off, no signal, and in just a second it turns off, and that can be delayed. When this is hooked up to, let's say, watching a movie, it doesn't turn on and off during the movie. So now let's get focused in on the meters. Here we go, powered up. Right now we're sitting at 67.58 hertz. 11 volts, which we're measuring across this resistor that's down here, and we're looking for the lowest voltage on this meter, and this will tell us what the resonant frequency is of the speaker. That looks like it right there, 57.6 hertz. Either way I go, the voltage goes up. So 57.6 hertz is the free air frequency of the speaker. I'm assuming you can hear that. Now we're going to answer the question of why we need a speaker box and why speakers don't work well when they're just suspended up in the air. While suspended up in the air, as the speaker's running, it's creating pressure waves going in and out. There's pressure waves on this side going in and out. There are also pressure waves on the back side, and they're 180 degrees out of phase. So as this pressure wave goes this way, that pressure wave is going that way, and that results in canceling them out. So now we're going to show you why a speaker works better in the box when we eliminate half of those waves. We're going to zoom back out, and you'll see right down here we've got my test box. So I'm going to grab that speaker without touching the amplifiers. I want to make sure you can see that I'm not going to modify anything on the test circuit. Take the speaker and just put it onto that box. So now we're going to take the speaker, move it a little closer. You can hear how loud it is. And now, without touching any of the test equipment, I'm going to just drop it and place it on top of the box. And you should have heard the volume go up. Let's make a light little change. Now you can hear how loud that is. That is why we need speaker boxes. Now we're going to move on to the next test. Next, we need to determine the speaker impedance. You can think of impedance as the same as resistance, except impedance is in an AC circuit. Where resistance in a circuit does not change, impedance in a circuit will change with frequency. Our first step is to find the max impedance of the speaker, which will be at the free air resonance of the speaker. First, I will set the function generator to the free air resonance of the speaker. It may already be set there. Yep. You need to readjust it down to the lowest voltage here on this meter. And now we have the speaker set at the free air resonance. And now, since I only have two multimeters, I'm going to need to reconfigure these so that one is a voltmeter across the speaker and the other one measures the current through the speaker. So there we've got our meters reconfigured. You have 6 point. I'm going to have to write these numbers down. Here we've got, we'll call that 6.33 volts. And watching this one vary a little bit back and forth, I'd say we've got 0.23 amps. And now we can go and derive our speaker impedance with those numbers. The next testing we're going to do is to come up with the speaker Q. Now you may be wondering why we're looking at a small glass bowl. The speaker Q is related to damping. And we're going to use that glass bowl to demonstrate what damping is. When I strike the bowl, it rings, which means it has very little damping. Now light pressure with my finger on one side of the bowl results in it not ringing, and that means it is damped. In most cases, it is not preferable for the speaker box to result in ringing or sounding like an echo chamber. In those cases, the box is underdamped. So now let's get back to the testing. Now we're back on the bench. We have our 2 meters set up. This one's going to be measuring the frequency out of the frequency counter. This one's measuring the voltage. I apologize for the pause, but I failed to fully explain this next test in the video. The next thing to calculate is the driver Q. Driver Q is how well the speaker is damped at its resonant frequency. The term damping is essentially something that inhibits continued oscillation, similar to the shocks that inhibit a vehicle from bouncing after you hit a bump. Another example is something that rings like a bell. That custard cup rung like a bell when struck, but when I put my finger on it, the oscillation was damped. For subwoofers and low-end drivers, it is preferable to have a low Q. First step is for some calculations to enable finding the 2 frequencies above and below the resonant frequency where impedance equals 0.707 times the max impedance. In the previous test, the voltage and current at the speaker was 0.23 amps at 6.35 volts. Using Ohm's law, ohms equals volts divided by amps equals 6.35 divided by 0.23 equals 27.6 ohms max impedance. Now, 0.707 times 27.6 equals 19.51 ohms. Now for the target voltage for the test,
Volts equals amps times ohms equals 0.23 times 19.51 equals 4.48 volts. And now, back to the bench.
So we're going to set this up. It should already be set up with the correct frequency, 57.6. 6.35 volts was previous, but this is close enough. So now we're going to find the two thresholds at 4.48 volts. First going down. .46, we're close close enough. 44.7 hertz. Make a note of that. And now we're going to go up. Again, we're looking for 4.48. Close enough, 67.4 hertz. And that concludes this part of the test.
Now that I have the two frequencies, I will label them F1 and F2, where F1 equals 44.7 and F2 equals 67.4. From previous tests, the free air resonance is 57.6 hertz. We'll call that Fs, and the max impedance is 27.6 ohms. Now, let's move over to Excel for the calculations. As I enter everything into Excel along with the formula, we come up with a speaker Q of 0.7355. Next up, we'll calculate what is called VAS.
Okay, we're back on our test bench, and we're ready to get our last number needed to calculate for our speaker. And just a quick review again, over here we've got our function generator to run a signal through the speaker. Going to be monitoring the hertz so we can measure the frequency. Down here is the resistor. We're going to be measuring the voltage drop across that resistor to find the frequency of the box. And of course my amplifier to drive the speaker. Up here we still have the speaker suspended in the air. You can see right there, there's my driver, and this is the test box. And now let's get set up to actually run the test. Now we're ready to get this test completed. Down here we've got my two meters. One on the left is set up to measure the frequency. The one on the right is set up to measure the voltage drop across that resistor right down there on the bench. And right here we've got my frequency generator, of course the amplifier, and up here I still have the speaker hanging on a string. We're going to drop this speaker onto my test box and then go on with the test. Now that we're positioned a little bit better, let's get everything powered up. This one will be measuring frequency. This one will be measuring voltage. Let's get our amplifier powered up, and you should be able to hear the speaker humming. Well, right now we're at 68 hertz. Taking a look here and making sure nothing has changed. There's our free air resonance. Now let's get this moved over. You'll see what happens when we drop it onto the box. And we should hear a volume change of the speaker. Volume didn't go up much, but it's a deeper tone. Next, I need to get the bracket down to put some pressure on here. Okay, this is so I don't have to drill holes in here, mount the speaker. Underneath here we have a foam strip for an airtight seal, and of course the gasket on the speaker, making certain we've got a nice tight seal on here. So now we're going to be searching for the frequency resonance of this box. Now while we're listening to that, let's get down here. And watch our meters. And we're looking for voltage on this one. There you hear the volume coming up. As the volume goes up, we're reaching the resonance of the box. There is the lowest voltage we have here, and we have a box resonance of 68.76 Hertz. So there is our last test. So now let's get going on with the calculations.
Now that we have the last number, we can go back to Excel to finish the calculation. By now, you've got to be wondering what we're going to do with all those numbers. I obtained this Excel spreadsheet from www.diysubwoofers.org. It will provide a recommended box size as well as calculated response curves. It also allows the ability to enter a custom box size to see how the performance might vary from its recommended box. I am not 100% familiar with this worksheet, so forgive me if I'm a little clunky going through it. We start on the alignments worksheet where the speaker parameters are entered in all the green cells, and then down below are a few more cells to enter the desired box parameters. I have already entered all of my speaker parameters from the testing as well as the volume of my box at 21.1 liters, the number of ports in the box, and the diameter of the port. The other two are left as defaults as suggested by the instructions. As you can see here, many of the cells have a tooltip pop-up when hovering that explains what it is. There is also an extensive Word document with instructions. Now we'll scroll down to see the table with calculated results. At the bottom of the table is a row named Optimum, which are the calculated values for the best box parameters for this driver. One of the things to look at is the F3 column, which is the 3 dB cutoff point. This is the frequency where the output of the speaker drops off significantly. As you can see that since I'm using a much smaller box, the cutoff frequency will be significantly higher than the optimum size. Now jumping over to the Comparisons tab, we can see the difference between the optimum size box and the box I'm going to build. These tables also provide a recommendation for the port dimensions to achieve the desired resonant frequency of the box. There are two rows. Desired, which is based on the Alignments tab, and Test 2, where you can alter the number of ports and diameter to see what lengths suit the box. Too small of a diameter or a port length that approaches the inside face of the box can result in port noise. In the charts, the blue line represents the optimum design and the red lines represent the box to be built. There are two lines for each design, where the thick one is without filtering or compensation. Since my design will have a subwoofer driver, I added 3 dB gain on the active equalizer. The lower chart shows the transfer function, which is based on the listening environment. I do not have the equipment required to measure the transfer function, so that is going to be ignored. Now that all this is done, it's time to go make some sawdust. Be sure to subscribe to follow this project and hit that notification bell to be informed of future updates.